Hey seniors, due diligence and recognizing the deficits and the unforeseen circumstances. I think the best path forward is to repeat the lesson, get you guys a recorded lecture of this, and try to dive deeper and hit some of the points that we missed based on the assessment. So let's jump into digital fluoroscopy as it's presented in Bouchon, chapter 26. All right, so digital fluoroscopy is obviously it's different than conventional fluoroscopy. So it includes the first iteration of digital fluoroscopy was let's replace the television camera and the film cameras that we had stacked on top of the image intensifier, and let's replace those with the first iteration of the digital camera, which is the CCD. But then since we've evolved and replaced with a flat panel detector, and so it's like first and second generation digital fluoroscopy, but we're doing different things because we are digitizing the image. And so that gives us powerful tools, gives us the ability to manipulate the image data via software. And so those are clearly advantages. And then usually with an upgrade in image receptor technology, you usually get a lowering of dose, and that's also true with digital fluoroscopy. So we're going to talk about a digital fluoroscopy system, not all of them built the same. Again, you can have an image intensifier system that's been converted to digital fluoroscopy by just including a CCD on the output phosphor rather than a conventional television camera. We're going to talk about the advantages of a flat panel image receptor over an image intensifier, procedures for temporal and energy subtraction. Okay. All right, so again, early versions of digital fluoroscopy use the conventional fluoroscopic chain. Now, what does that mean? That means an image intensifier, but added an ADC and a computer between the camera tube and the monitor, and then we replace the camera tube with a CCD. Okay, so we got to figure out what that analog to digital converter is. This is critical to your understanding of digital image formation. An ADC is a device that divides the video, which is analog signal, it's visible light, okay, into a number of bits, that is strings of information, okay? And what it really is doing is it's subdividing the picture into tiny little sections. Okay, similar to what we learned in CT, it's dividing the picture into a matrix built out of picture elements or pixels. Okay, every digital imaging device does this. It breaks up a bigger macro image into very tiny images all mashed together. That is the essence of digital imaging. The colors we assign to those picture elements can be represented by binary code, ones and zeros, okay? And so we can display it visually on a monitor, but also we can manipulate it with a computer program. So the ADC is critical to digital imaging and taking what is a visual piece of information and turning it into an electronic piece of information, or a string of data to be interpreted by a computer. Okay? And so the ADC is revolutionary, as well as the CCD being revolutionary. Okay? So both of these components, but an ADC can take any visible light source or any analog source and change it into a stream of ones and zeros, a stream of electrons, essentially. Okay, we're going to see the ADC is utilized not only in digital fluoroscopy, but also in conventional digital imaging, there's an ADC that is in between our control console and our flat panel image receptor in the DR system. There's also an ADC inside the CR reader. So this ADC device is basically a fundamental component of a digital imaging system. All right, so a conventional camera basically captures light and is able to transmit it to a broadcast monitor. Back in the day, that was a cathode ray tube. In the modern era, that is an LCD monitor. Excuse me. Okay. So the CCD, which debuted somewhere in the early 70s, started replacing the camera tube because the CCD is actually a more efficient camera than a conventional motion picture camera tube, which is called the Plumicon or the Vidicon. Now, they used to ask about the Plumicon and the Vidicon on the credentialing exam, but because it's been out of use for so long, I don't think they're going to ask about it. They're going to focus on the CCD, which is first generation digital camera technology, the CMOS slightly because that's second generation digital camera technology, and then finally we get to, after the CCD and CMOS, which were built for visible light, by the way, then we finally, somewhere in the late 80s, early 90s, we finally get a specific digital imaging system for radiography, not just, replacing photographic film and visible light pictures. We get a digital camera specifically built to capture X-ray beams or X-ray images, okay? We'll hear more about that in digital imaging, okay? So the CCD is the first generation of what we would call a digital camera, okay? It is more light sensitive than a old style television camera, the Vidicon Plumicon concept, which Bouchon, I think, still has the illustration in his book and a brief description about those, but those are obsolete technology. So I think it's safe to skip over those. The CCD is more efficient than previous technology. There's less noise associated with operating a CCD. And there's no spatial distortion. The trouble with the Vidicon Plumicon is it's got kind of a fisheye lens or a pin cushion type distortion where the far corners are kind of warped. It kind of presents what would be a flat image, kind of presents it as kind of a convex curved image, okay? And so you get stretching and distortion at the edges of the old video camera, the old television camera. But because the CCD is a flat technology, it doesn't, we've engineered that distortion away because we don't have any curved surfaces on the CCD. As far as the light capturing surface is completely flat. That wasn't the case with the Vidicon or the Plumicon. So we don't get the stretching of the image at the corners like you would with an old style television camera. Okay? It has a higher spatial resolution because of the way it subdivides the image into very tiny images. Okay? Because it has a higher DQE, that's detective quantum efficiency, it doesn't require as much radiation as we used to need with a conventional television camera. So the amount of stimulation that a CCD needs in order to make a picture is quite a bit less. It's more sensitive to light, and so it needs less light. Well, that means the output phosphor doesn't need to be as bright. Well, that means that the photocathode doesn't need to shed as much electrons. That means that the input phosphor doesn't need to produce as much light. That means we don't have to send as much X-ray. See how I logically deduced backwards? Because the final image capturing sensor is more sensitive than previous technology, we can get away with a weaker signal, a weaker remnant beam, and still get a good image. So it's basically improving the efficiency of the image intensifier. All right, so our CCD, our first generation digital fluoroscopy, see how it says image intensifier and then the CCD stacked on top? That CCD is connected to the output phosphor via fiber optic cables, okay, or fiber optic wire, okay? So fiber optic wire is a polymer plastic that behaves funny with light. It's shaped like a cylinder, it's a flexible cylinder. If you put a light photon in the face, the entrance face of that cylinder, the photon has total internal reflection. That means it doesn't come out the sides of the fiber optic cable. It's stuck inside the fiber optic cable till it gets to the other end of the cylinder. So fiber optic cable is a neat little way to bend light and steer it to exactly where you want to. It's like a hose for light, is what it is. Okay? And so that's very handy. We have light coming out of the output phosphor. If we tether the output of the, if we glue fiber optic cable and cover the surface of the output phosphor with fiber optic cable, and then we bundle these fiber optic cables and glue the other end to the CCD, then all of the light coming out of the output phosphor will be trapped in the fiber optic cables and will deposit onto the face of the CCD. And so we won't have any loss of the information. None of the light will drift away in a random direction. So it improves the efficiency of the transfer too. Okay. So now it says image intensifier or flat panel image receptor. Now that's a flaw in Bouchon's diagram. What is important to know is if you switch to a flat panel, you don't need a CCD. The flat panel third and fourth generation technology that you're going to talk about in digital imaging in detail replaces the image intensifier CCD. Okay? The CCD was replacing the conventional television camera. The CCD is your camera phone. It's the light sensitive chip behind your camera phone lens in your cell phone camera. Okay? So it's sensitive to light. It doesn't catch X-rays. The flat panel image receptor does the job of both the image intensifier and the CCD. And so that's part of the reason I don't like this illustration is it doesn't give you that extra it omits that detail that you don't need a CCD if you have a flat panel DR or digital fluoroscopy system. Okay? And so the next thing to do is to jump into, and I hope that's what we do, is jump into how does a charged coupled device work. So about 1969 is where they figured out this charged coupled device. All right, sorry guys, had to step away for a second. So charged coupled device, 1969 is when they figured out how to make silicone, pure silicon is able to catch light photons and create a voltage across the silicon wafer. And so it's called the photovoltaic effect. It's how solar panels are made. But what they figured out is they could make a solar panel that understood what light it was capturing. That is, we could divide a solar panel into a grid with very, very tiny grid elements, and each grid element would catch its own photons. And so we could tell the difference between bright areas and dark areas on the solar panel. That's essentially what a CCD is doing, okay? So the CCDs, the photons come in and they hit this silicone layer. What that's going to do is it's going to create a separation of orbital electrons. It's almost like ionization. There's a separation of valence shell electrons from the silicon atoms. Okay, that's the photovoltaic effect. Dependent upon the environment, so when you have beach sand out there, the beach sand is doing this. The beach sand is participating in the photovoltaic effect. But what happens is the electron just grounds back out to the positive ion. But if you have this wafer of silicon where you have a layer on top of it that is like an anti-static layer, that's the dielectric layer, it can actually pick up and absorb those loose electrons before the silicon has a chance to self-neutralize again. Okay? And that's the science of a solar panel, and it's also the science of a CCD. So that's how the CCD is capturing the light, so to speak, is the silicone is shedding. When the silicone is hit by light energy, it sheds its valence electrons. Those would ground back out into the silicon, but before they can do that, they're pulled away by this anti-static layer. Okay, so as the silicon absorbs light, it becomes effectively positively charged. Okay. Now, if you have the underside of the silicon coupled to capacitors, then those positive charges will drift down onto the capacitors. Okay. The positive charges will drift until they find electrons. Okay. And so you have to kind of trick those positive ions to staying on the capacitors, and that becomes clear when we look at the schematic on the next slide. All right, and so you funnel these positive ions onto these capacitor plates, but then you have control capacitors or gates on either side of those, so the positive ions don't really have anywhere to flow. Okay. The gate can be open, very much like a gate to a herd of cattle. The gate can be opened and closed by controlling the gate circuit, which is all the way on the bottom of the CCD. So when we open the gate, it allows the positive ions to run out of the capacitor into the next area. And so let me show you that on the CCD schematic. Okay, so here we have the schematic, right? Now, Bouchon, you might notice that all the words are upside down, and that's because the CCD, the light-sensitive layer on a fluoro tower, the CCD is turned upside down because the X-ray is under the table. The X-ray comes up through the patient, hits the input phosphor, hits the photocathode, turns into a stream of electrons, all of this traveling upward through the room. The electrons are focused, hit the image intensifier, and then the output phosphor. The output phosphor starts glowing, and those light photons are sent up toward the ceiling. So that's why Bouchon has his CCD upside down, is because he wants the light to come in from the bottom, because that's how it is in a conventional fluoroscope. So I've turned it upside down because Well, that's how I'm used to looking at the schematic of a CCD. So bear with me that these words are upside down. So the light comes in. There's an anti-scratch coating on the front of your silicone wafer, okay? And then there's an anti-static dielectric layer, okay? The yellow part is where the photovoltaic effect is happening, okay? So when light photons pass through the first two layers, they end up energizing the silicone, and then we get ion pairs forming. The dielectric layer vacuums up those loose electrons before they have a chance to ground back out with the positive ions. So the net effect is the silicone starts to become positively charged. Well, that's not stable, so it starts looking for donor electrons elsewhere. And that's where those charge electrode pixels come in. The charge electrodes are tethered to capacitors, and that capacitor is tethered to the ground, okay? So effectively, the positive ions pick up loose electrons from the charge electrodes, and then the charge electrodes become positively charged. And then those positive charges start stacking on the capacitor plate that they're tethered to. Now, why would the positive charges start stacking there? Well, it's because the other side of the capacitor is connected to a ground. And so I need you to remember back to what I taught you about schematics. Capacitors are temporary storehouses of charge, like a temporary battery. And so grounds are infinite reservoirs of charge. And so if the electrodes and the capacitor, the top plate of the capacitor, start to collect these positive charges, the ground will start donating electrons on the negative plate of the capacitor to hold the positive ions in place, okay? And so the capacitor starts building charge because the ground is acting as a ballast to the positively charged electrodes, okay? You have to consider the positive plate of the capacitor and the positively charged electrode kind of as one element, like an anode, okay? So those positive ions are stuck there. Now remember, every positive ion stored is the result of a photon strike. And so more photon strikes means more positive ions are stored, okay? And now to the immediate right of that full capacitor that we see it looks like a capacitor, but what that actually is a transistor. It's a field effect transistor. And you see down here where it says gate pulse, it's upside down, it's in the bottom purple section. That's an independent circuit that is providing control to the gates. If we turn the current on for the gate pulse circuit, then the gate swings open and those positive ions can move through the gate, okay? And so they will move, in this diagram, they will shift to the right, okay? And so what we end up doing is we end up doing like a old-time bucket brigade. So back in the day, to put out a fire, you would have a water tank on wheels drawn by a horse, and you would have a pumping mechanism, and then all the neighbors would bring out their buckets, okay? And so the house would be on fire. You would fill a bucket right there at the pumping tank, and then you would turn with your full bucket and dump it into your neighbor's bucket. and then you would turn back and fill your bucket again. Okay? And so your neighbor would take the full bucket and dump it into the next bucket in the line. And every neighbor would transfer the water bucket by bucket from the pumping tank to the house that was on fire. And so when the last neighbor in line got the bucket full of water, they would run into the house and pour the water on the fire, and then run back out, and then the next neighbor in line would have a full bucket again and refill their bucket. And that was called a bucket brigade, and that's how you used to put out house fires, is all the neighbors in the town would work together to transfer the water from one bucket to the next, to the next, to the next, all in a row, until you had a bucket that would douse the fire. That's exactly how the CCD is moving the charges off of the pixels. Row by row, we're shifting the positive charges from one storage capacitor to the next row of pixels over, until you get to all the way at the far right hand side of this diagram. The last row of pixels always dumps their positive ions to the charge amplifier. Okay? And so the charge amplifier, basically it's boosting the current. Okay? So it functions very similar to a step-down transformer. Okay? So a bolus of charge comes in, the charge amplifier amplifies the current, right? And then that's sent to an ADC right off of the charge amplifier. So how do we get the third row of pixels to get to the charge? Well, the third row of pixels shifts the charge to the second row of pixels. Why is the second row of pixels capacitor empty? Because they have shifted their charge to the first row of pixels. Well, why is that one empty? Because they have already dumped their charges to the charge amplifier. So very much like water moving through the bucket brigade, the positive charges move row by row sequentially from the second row of pixels down to the first row of pixels, and then off onto the amplifier. Okay? And that's the better explanation for how a CCD works. All right, so this part here, so from left to right, there's the full storage capacitor with a grounded negative plate. So the ground is donating those electrons just for the sake of parking those positive ions and holding on to them. That's why it's called the storage capacitor for that particular pixel gate electrode, which is the red. Okay? So those positive charges won't move until the next device over to the right, which is the transistor, offers a greater negative charge than the ground is offering. Okay? The ground is only offering a balance of charges, okay? Because that's all the ground will ever offer. So if I have 3 positive charges stored and I want them to move through the gate, I'm going to supply the gate electrode, which is that flat thing, right? There's like a U-shaped wire and then a little flat thing. That's the gate electrode. I'm going to supply that with 5 negative charges or 10 negative charges. And then the Coulomb force on the positive charges will motivate them to move away from the measly 3 negative charges and move toward the 5 or 10 or whatever more negative charges on the gate electrode. And so that's how we get those positive charges to shift off of the storage capacitor. But they won't do that until we supply a current to the gate electrode. and stack negative charges on the gate electrode. Okay? And so you can see that the schematic repeats itself after that point. So after we get those positive charges to move to the gate electrode, that's a one-way street. Okay, there should be a diode in there, but it's simplified. Okay, the storage capacitor over to the right in the first row is now empty because it did the same thing, and that ended up dumping the positive charges to the amplifier. So now that storage capacitor is empty. Okay. Now if we turn off the gate electrodes, now those positive charges want to drift to the next available storage capacitor, which is the one in the next pixel over. Okay, the one that's indicated there with half of the word capacitor. Okay, and so again the process repeats itself. The ground supplies a balance of charges to hold on to the positive charges that have migrated over, okay, until we're ready for readout. When we're ready for readout, we supply a gate voltage to the transistor, which is to the immediate right of the storage capacitor. It's more negative charges than what the ground is supplying, and so it's a stronger Coulomb force, and so the stored positive charges move through the gate and end up in the amplifier. Okay? The ground supplies and donates charge as necessary by what you would call, in a capacitor, what you would call static voltage or Coulomb force. And so it's only enough to balance what's being held, but it's not enough to keep it there once a stronger external motivator is applied, and that's applied at the gate electrode. All right, I'm not going to repeat this video, but this video, there's a reason I included this. Watch this video over and over and over again, because he shows you an animation of the bucket brigade method, pixels read out row by row through this. This is Bill Hemmer, the engineer guy. This is an amazing video. You have to watch this video and understand how this bucket brigade action works, because that's also how we read off a flat panel detector in digital imaging. So understanding this helps you for this unit, this class, digital fluoro, but it also helps you for digital imaging next semester. All right, let me pause that just a second. All right, so what does a charged coupled device give you? Well, we get a higher spatial resolution. We get a higher signal to noise ratio. Now, signal to noise ratio, what is signal? Signal is the intended data, right? So, and I gave Ali the example of like tuning into a radio station. You want to hear the song. What you don't want to hear is all the crackles and pops when the station is starting. You're getting too far away from the broadcast tower. Like say you're going to see a UT football game, you're heading over to the mountains, you're going hiking in the Smoky Mountains. Oh, I'm so jealous. Anyway, you're driving away from where the radio tower is. And so what happens is the signal starts to get weaker and weaker and weaker. That's the inverse square law. You know that already. Okay? Yeah, it works with radio towers too. So as the signal gets weaker, there is noise always, but your radio can ignore that because it's so weak. Okay, in the same way, a really efficient image receptor can ignore noise, or noise can be minimal if the signal is just ridiculously stronger than the noise. So a good signal to noise ratio is just basically, it's just good broadcasting. We want to capture the intended signal. What's the intended signal? The X-ray picture or the fluoroscopy picture. That's the remnant beam. We want to see what the remnant beam looks like because that's how the image forms. What we don't want is all the random stuff that happens while we're trying to make the random, like Compton scatter, internal electronic noise of the devices we're using in the image receptor technology. All that kind of stuff is randomness, like drifting into the intended signal. Okay? So the CCD had improvements in efficiency from a conventional television camera. So it's got a better signal to noise ratio. It doesn't generate as much noise as the old television camera technology did. Okay? High detective quantum efficiency. Now this is a digital imaging term. You're going to be quizzed on this in the next class in digital imaging. Detective quantum efficiency is how good is my image receptor at catching photons. In the case of CCD, it's light photons. Okay? But when we think about it as far as digital X-ray technology, typically detective quantum efficiency is how good are we catching, how good at catching the remnant signal is this image receptor technology. And it's usually expressed as a percentage. So I'll give you a quick example. Cesium iodide indirect DR flat panel, the Canon DR plate that you're used to, it's everywhere. You're used to working with this thing. How efficient is that at catching the remnant beam? Somewhere in 60 to 70% typically. It comes in about 63 to 66% is what most publishers say. Okay? And so that's 2/3 of the photons in the remnant beam. Now, how good is that? Well, it's about double as efficient as screen film technology and CR technology. Screen film at its best only captured 30% of the X-ray beam. I'll say that again. Screen film technology, what we used for about 100 years to make medical X-rays, only caught about 30% of the X-ray going through it. 70% of the X-ray just kept on going through the cassette. Okay? Now we capture about 66%, 2 out of every 3 photons. Okay? And so that's what detective quantum efficiency is. The more efficient the image receptor, the higher their detective quantum efficiency is. Okay? So we engineer these things to catch photons. How good are they at catching those photons? That's what DQE is measuring. Okay? So no warm-up needed. Typically your television camera actually had to get hot. There was part of it that had to get hot or warmed up. You had to pass current through it until the components warmed up, and then it could run just fine. And so there was a little lag with the technology as far as you got to turn the machine on and get it up to temperature, and then the component worked as described. Okay? No lag or blooming. Lag is a delay, obviously, in the capture of the image and transference of that image. The conventional video camera coupled with the image intensifier did have a lag time. Okay? Blooming is like a streaking artifact of brightness. Okay? And so, and it's part of it is the conventional television camera, but part of that was the CRT. Now the early CCD did suffer from blooming, but they re-engineered it and figured out how to fix the blooming artifact that would occur with the early CCD. It's like you have a bright object on your image, and then that bright object starts offering linear streaks through the image. Okay, that did happen with conventional television images. Whenever, like, there was an eclipse back in the day, there was always streaks involved. Anytime they tried to take a television camera, picture of the sun, it was always streaky and you always got these artifacts in the image. Those were blooming type artifacts, and that is what's to say is you're overloading the number of photons that can be captured by the image capture device. Okay, the early CCD, you could overload those. They're a little bit more resistant to overload, and the blooming and the streaking was spilling out of those extra photons into areas adjacent to the bright object in your picture. Okay. No maintenance. Our CCDs are extremely durable. They don't have moving components, not on the macro level. We shift positive ions around, but at the end of the exposure, everything is grounded out and returned to neutral charge. And so physical wear and tear is happening on the molecular level, but it's being restored to the previous condition. That is the starting point of the reaction. It's very much molecular or atomic engineering is what's happening with the CCD, but then it returns to a ground state at the tail end of the exposure. And so the CCD is basically not corroding or wearing out or doing any of the, well, it's a machine so it wears out because it's got moving parts and there's friction. No, none of that is happening in a CCD. So it's extremely durable. Okay. A CCD, typically the number one way a CCD fails is physical contusion. Okay, and you drop your cell phone. Okay, and so you crack. You offer physical stress to the thing from a drop or a collision or something, and then it tears the silicone wafer. That's how a CCD fails. Okay, but as far as using the thing and then eventually it breaks down like an automobile, no, it doesn't do that. Okay, so there's no maintenance to a CCD, and even if there is maintenance to a CCD, it really is just pull the machine apart, pry up the CCD because it's got connection prongs to a circuit board. So undo all the solder points, pry it up with a pair of tweezers, and replace it with a replacement CCD, and then solder it back to the circuit board. If you want to go through that trouble, it's extremely cheap to build a CCD. The components are, pennies to make this thing. So there's oodles and oodles of them just sitting in warehouses waiting to be installed in digital cameras. It's not worth the effort to replace or maintain a CCD and replace it as a component. So usually it's, the lifespan of the CCD basically outlasts the rest of the fluoroscope. Okay. Unaffected by magnetic fields. The early video cameras involved electron streams, and so Michael Faraday says you can deviate. If you apply an external magnetic field to a charge, you can make the charge move, and so that electron stream can be altered by a strong magnet. So that's one of the ways you sabotage early television equipment and early fluoroscopes is you bring in a strong magnet and it basically ruins the TV signal. Okay. That was also a prank you can pull on your grandmother with her cathode ray tube television back in the day. Linear response, one photon yields one positive ion, so it's really good at maintaining the contrast of the signal and preserving that contrast, because it is a one-to-one conversion from light photon strike to one positive ion is formed, and so you get a nice preservation of the attenuation differences recorded in what the CCD records, and the difference in light intensities that reflects the differences in attenuations of the various structures in the remnant beam. And so it does record that attenuation difference, and it preserves the subject contrast, if you will, with that linear response. And then because the thing is so much more efficient than previous technologies, you don't need as much radiation to stimulate it ultimately. And so we can get away with lower MAs for digital fluoroscopy, operate at lower MA stations than we did with previous technology fluoroscopes. Okay. So the more recent advance is, instead of just tacking a CCD with fiber optic piping to the output phosphor, is to get rid of the image intensifier altogether and just replace it with a flat panel detector. Okay? So the flat panel detector is basically the new technology. Flat panel detectors is basically we take the CCD and we improve it, and then we re-engineer it with a top layer specifically designed to capture X-ray, not visible light. Okay, and then we segment it a little bit better than a CCD does, and we provide individual data dump lines rather than bucket brigade technology. And so we improve the way that we basically unload the digital detector in third generation DR plates. The amorphous silicon, it's called an active matrix flat panel array, and it's got TFT arrays, and it's got gate control circuits, very much like, but it's got individual data dump lines, and the only one, so instead of one data dump at the end of the row, only one pixel will use the data dump line at a time. And so we don't get noise from one pixel affecting another pixel. Okay.
NGH School of Health Sciences.
And so you're going to learn, again, you're going to learn about the active matrix flat panel array, which is that second bullet point, the flat panel detectors. You're going to learn about those in digital imaging. There's two types, indirect and direct. So the indirect is basically the latest and greatest of the CCD, upgraded and made more efficient with dedicated data lines running through the matrix, not at the end of the plate, to reduce noise even further. And then on top of that active matrix, it's still amorphous silicone, which is, remember, that's the active layer for the CCD as well. But we have glued cesium iodide phosphor to the top of the amorphous silicone wafers. Okay, and so the cesium iodide, very much like the input phosphor, so basically we've taken the input phosphor from the image intensifier, and instead of going to the trouble of converting to electrons and then back to light, we just lay that input phosphor flat right on top of a big, like 18-inch by 18-inch CCD grid. That's what the flat panel detector essentially is. Okay. Now we will do a deeper dive in digital imaging. Okay. That's an indirect DR plate. It is third generation CCD technology that has been improved. It's been expanded to an 18-inch by 18-inch area, given separate data lines for each row and separate control lines for each column. And so the way we unload a flat panel detector is pixel by pixel, which does reduce noise better. Okay. and it does prevent blooming better. So the active matrix array is better than the CCD. The flat panel detector is better than the CCD because it's more careful with how it unloads its collected positive charges. Okay, it doesn't bunny hop them. It sorts them into their own separate conveyor belts, basically. Okay. Now the other way we have made an improvement, which is completely different than a CCD, is we've swapped out the silicone for selenium. Selenium does not get stimulated by light, it gets stimulated directly by X-ray. And so we've skipped a step, basically. The CCD relies on a light signal to create stored positive charges, which are mapped as pixel intensities. The indirect detector relies on cesium iodide to create light, and so it relies on light, not X-ray, to store the pixel intensities. But the amorphous selenium detector directly captures the remnant X-ray beam. It doesn't convert it to light first. Okay, so those are the two big types. They work in fluoroscopy just as well as they work in X-ray, and they're basically the same image receptor technologies. Okay. The dynamic digital detector, you just need faster readout and faster on-the-fly processing of the image. Okay. And so you beef up the readout and processing electronics for a fluoroscope, and it basically is able to broadcast the images in real time rather than like on a digital flat panel plate like the Canon plate. It takes about 2 seconds to get the flat panel image. We just beef out the software readout electronics and make them quicker. Stack amplifiers have more, maybe instead of one ADC converter, we have an array of ADC converters, one for each row, so that all the rows can be read out simultaneously and go to separate inputs in the computer. And you can process, instead of process like a flat panel detector will process image intensities one row by one row and save those pixel intensities, the first row, then the second row, then the third row. It does it really fast because it's doing 5 billion calculations a second. In a dynamic fluoro array, it's the same technology. We're just finding faster ways to read out the pixels. And so we can get an image downloaded from that image receptor and processed and displayed in thousands of a second rather than 2 seconds for the DR flat panel. Okay, and so it's just speeding up the readout of electronics with the dynamic detector. Actually catching the remnant signal, it's the same technology for a flat panel plate like the Canon plate on the portable machine as it is for the flat panel fluoroscope. All right, back again, guys. I interrupted again. I do apologize. All right, so the dynamic detector, nothing's changed about the technology about how it captures the X-ray. What is changed, and what I said on the previous slide, is how fast it can rapidly read out a set of full pixels. So we shower the detector with X-ray photons, right? And then dependent upon whether it's direct or indirect, those are converted to light or are absorbed directly. And what ends up is we end up, again, just like the CCD, storing boluses of positive charge on individual capacitors for individual picture elements, okay? But when we beef up the readout electronics, we can actually take a new picture with a dynamic detector system 60 times a second. Okay? And so that's the fundamental difference between a flat panel fluoroscope detector and the flat panel DR image receptor that you're using in conventional radiography is how fast can it read out an image and broadcast an image to a monitor. The digital fluoroscope can do that 60 times a second, okay, which is very impressive. And I did mention this when I covered this the first time. The human eyeball is, as far as visual acuity goes and being able to take in information, it's got limitations to it. And one of the limitations is it can't tell the difference between rapid still frames and fluid motion, okay? And so, and I alluded to this with video game players, 50 frames per second kind of looks like strobe light. It looks choppy. The motion is like stilted or in chunks, if you will. But once you kick it up to 30 frames per second, about somewhere between 97 and 99% of the population is fooled into thinking that's fluid motion. And in fact, if we look back to motion picture film and Edison inventing motion picture film, that's how he did it. He took several still pictures, still photographs, but he moved them past the projector they were on a reel, and he had a motor moving the pictures past a flashlight, essentially. And so there was an incremental change from one picture to the next, to the next, to the next, to the next. But when you change out those pictures fast enough, the human eye thinks that it's fluid motion, okay? And so that's essentially what we're doing with our flat panel digital fluoroscope, is we're pushing new images to the monitor so rapidly that the human observer thinks that that's fluid motion, when in fact it's actually 60 still pictures presented so rapidly that the changes look fluid, okay? And so once you get past that 30 frames per second, 30 individual images, so image A, and then 1/1000th of a second later, now it's image B, and there's a slight change, and now it's image C, and there's a slight change, and the images are being swapped out on the monitor so fast that it looks like motion to you. It looks like fluid motion to you. It looks like dynamic, real-time, real live movement, okay? So the flat panel, it says the flat panel is designed as two-dimensional, rectilinear. What the heck does that mean? Well, they just said it was flat panel, so flat implies two dimensions. So it's just another way to say it's flat, okay? Rectilinear array means the pixels are arranged in a geometric format, rows and columns of pixels. In other words, a matrix, okay? That can electronically be processed line by line in a fraction of a second. Remember, I did mention the CPU, the central processing unit, has 5 gigahertz clock speed. What does that mean? It's 5 billion computations a second. So our computer brain can read out the pixel array. So let's say in one row of pixels we have, let's make it something ridiculous. We got 1,000 pixels per row, and then 1,000 columns of pixels too. Okay, that's 1,000 by 1,000. What is that? 1,000 by 1,000 is 1,000,000. Okay, the computer can read out 5 billion pixels per second, because that's a simple computation. Tell me what the intensity of this block is, this little square is. Read out the stored charge. Okay, that's a simple thing. So to the computer as simple as calculating 2 plus 2. Okay? And so even with a 1000 by 1000 pixel matrix, 1000 rows, 1000 columns, 5 billion versus 1 million. 5 billion in a second. Okay? So how many millions do you need to get to 5 billion? Well, you would need, I think 500,000 sounds right. Let me do the calculation quick. Hang on. No, it's not 500,000, ladies and gentlemen, it's 5,000. So you have computers that are capable of reading 5,000 images per second. So 60 images per second is not a big deal. Okay? It can read out at a clock speed of 5 gigahertz. Okay? It does computations at a clock speed of 5 gigahertz. And so even if we have 1 million pixels in our pixel matrix, right, it can do that 5,000 times. If it's just reading out the value, it can do that 5,000 times a second. Okay? So in other words, it processes really fast. Okay. So low noise. Noise is trouble in digital imaging. And not, you're thinking scatter radiation because you were taught well by Mr. Shepard. Yes, Compton creates noise in the remnant beam, but we're talking about electronic noise. When you operate an electronic device, it generates its own internal noise. What is that? Well, it's like phantom resistances that you weren't expecting. Or sometimes they call those eddy currents. What's an eddy current? It's a current that flows in a circle, or it flows against the flow of the intended current. Okay? And so you'll have eddy currents. When eddy currents form, rather than the electrons transitioning down the circuit line in a linear fashion, the electron will just spin and loop back around, like on the wire or on the circuit channel or whatever it is. And so the electron won't really go anywhere if it gets caught in eddy current. Okay? And so eddy currents are things. Those things happen to electricians. Electricians are familiar with eddy currents, and they're familiar with principles of resistance and native resistance of electric circuits. That is, anytime you operate an electric circuit, it's pushing the components that you use push back against the intended flow. Okay, so you intend for let's say you intend the electrons to flow left to right, right? Resistance means that because you're using wires and because you're using molecules to bunny hop these electrons along, the molecules and the wires are going to push back. And so part of the noise is the components that you're using are encouraging the electrons to misbehave and do random stuff rather than do what they're supposed to do, which is follow the voltage, the pole of the voltage. Okay? So when we design, not us, but the electrical engineers that build these things, when image receptors are designed, it is an integrated circuit device. It's got electrical components in it, and those have electrical noise or random motions of electrons. Okay? Well, if we don't engineer correctly and put in circuit controls to keep noise, electronic noise, at a minimum, then we'll get very noisy images. So what you're figuring out here and what you're going to be quizzed on again in digital imaging is that there's more than one source of noise once we turn this thing into a digital image. In screen film, there was only one source of noise, and that was the Compton scatter. But now that we've converted the image into electronic form, computer circuit form, computer data form, it's subject to electronic noise too, in addition to X-ray noise, which is Compton scatter. Okay, and so The noisiness of detectors is a factor, okay? And so application-specific integrated circuits, that is, the way that you engineer the circuits that are in the pixel matrix, can help correct the noise generated by the pixel matrix, okay? And so those are included in all flat panel detectors, but the application-specific integrated circuits, that is extra components that we add to eliminate noise, those are more important for digital fluoroscopy because they make the image receptor more efficient, and they actually boost signal to noise ratio and improve the efficiency of the image recepting components. Okay. All right, so the first advantage of upgrading from image intensified with CCD coupling to pure flat panel DF is the flat panel tower is smaller. It takes up less room, and it doesn't weigh as much as an image intensifier. Okay, so it's not as bulky, it's easier to fit into a room. You could potentially fit into a little bit smaller room. You just still got to have room for the table, but it doesn't take up as much space as an image intensified fluoroscopy unit does. Okay, it's also easier to steer around because it's not as heavy as the image intensifier is. Okay. The image intensifier had to have a lot of accessory equipment tethered to it before the invention of the CCD, like a spot filming device, a cinematic camera, like with a film spool, all those types of things, a beam splitting device. You can see those in chapter 25. Those are basically obsolete now. The CCD did all of that, and now the flat panel detector does all that. So there used to be a thing called spot filming where you would actually insert a cassette. There was a cassette slot in the fluoroscope tower, and you could swap in a cassette to take a conventional X-ray, and then it would eject the cassette, and then you could run that spot film. When we went to digital, that spot film cassette device basically became obsolete. Okay, and so you can do the flat panel detector, and the coupled software replaces all of those things that were necessary coupled to the regular television video camera. So the spot film imager was coupled. We don't need a separate spot film imager anymore. The flat panel detector can take a conventional X-ray just as well as a motion picture X-ray. And so it can swap to a still image processing software rather than motion picture processing software. It can record a cinematic loop and like do a run where it loops video in playback until you stop it and activate fluoro again. It can do last image hold, which is actually a radiation safety measure. It's a radiation savings. It used to be when you took your thumb off the exposure switch that the television screen would go black, but last image hold freezes the last still image that you took in when you had live fluoro. Now when you let off the button, it kind of gives you a still image of the last thing that you were broadcasting, the last frame that you were broadcasting. And so that actually saves radiation to the patient. Okay. You can do post-processing. don't get degradation. Very much like there's no real moving components to a CCD, there's really also no moving components to a flat panel array. Okay, and so again, the same advantages that a CCD had over a conventional television camera, the flat panel detector has the same advantages over an image intensified system. Okay, so durability, no moving parts, so no parts to wear out, break down. Great contrast resolution. It preserves the attenuation differences, and it's a one-to-one transfer again of conversion of that X-ray photon to ultimately a stored positive charge on a capacitor in a pixel. That's a one-to-one conversion. So when it counts positive charges in those, each one of those positive charges that it's stored is basically representative of one X-ray photon. Okay. Higher detective quantum efficiency. Again, I mentioned that previously. I talked about what DQE was. With our flat panel arrays, the indirect ones pull about 60% of the remnant beam and capture it. So that amorphous selenium is a little bit lower. It's somewhere in the mid-40s, I think, but it's still higher than screen film technology or conventional image intensifier. Okay. Wider dynamic range. Dynamic range is the ability of the system to display shades of gray. Typically your digital software systems have dynamic ranges in like tens of thousands. Like it's not unheard of to have the software is capable of displaying 30,000 different shades of gray. Now it doesn't actually display the entire dynamic range. It displays the grayscale, which is a section of the dynamic range. And typically the grayscale is somewhere around the limits of human vision, which is, I told you before, 15 different colors or shades of gray is all the contrast we can stand, okay? Or all the contrast range we can stand. So we have softwares that are capable of producing dynamic range images with 30,000 shades of gray, no problem. But the problem is if you put that on the monitor, we'll only be able to see about 15 different shades, even though there's actually 30,000 shades there. Okay, but that we'll speak about that in digital imaging. That's where AI comes in. A computer can actually see, a computer software can see more shades of gray than we can, and can detect aberrations, if you will, in the picture that a human eye couldn't even see. So a rectangular field versus a circular field. Yes, the flat panel array along with the CCD, both of those are rectangular matrices. Okay, not exactly, most of the time exactly square, but not always. But we don't round, the image intensifier definitely has to round off the corners, and so you lose the corners in the monitor if it's image intensified fluoroscopy, whereas digital fluoroscopy with a flat panel detector, it broadcasts a rectangular image matrix. Okay, and so you don't round off the corners, and therefore you display more anatomy. Okay, with a particular live fluoro run, you display a bigger area of the tissue of the patient. Okay. The other advantage is we can tweak the brightness and contrast of like a cine run, a still image. We can do digital subtraction because that's a software package, that's a software correction. We can do all the post-exposure manipulation we can do with conventional digital images. We can also do this with digital fluoroscopy too. Okay. Usually what it is you pause the run and then you make the change to one frame of the run. Like if you're playing a motion picture loop, a cinematic loop, You make the changes that you want to brightness and contrast, or maybe you zoom in to a certain area of it, and then it'll apply your changes to all of the frames in that loop and then play the loop in real time. So, and then again, north of 30 frames a second, it fools you into motion picture. So, and then typically, again, we are across the board from obsolete technology, we're doubling the efficiency of the image receptor. That's just baseline. Now, some of the DR technology is more efficient than others, but just for baseline, on average, we're doubling the efficiency of the image receptor at catching the X-ray, and so therefore we can use half the amount of radiation and still get a good image. And so as digital fluoroscopy is taking over, it's basically about 90% of the way there. We're seeing dose reductions to the patient as we perform these exams versus the same exam that their parents or their grandparents had to go through. A dose savings of 50% is fantastic. So, okay, binning. Hang on. So binning is something that happens with fluoroscopic images and those rapid frames. One of the ways they shortcut building an image is you might have like a 10 by 24 by 1024, but again, capitalizing on the way human vision works, you're not going to see the details. Hang on just a second. My goodness, we've been busy today. All right, so the shortcut we can create with binning. Remember how we're trying to push at least 30 frames per second? Well, what it can actually do, what the software can do, is it can take the individual pixels that are adjacent on the image matrix, like 4 of them, and basically bundle all the charges together into one stack. Essentially, making those 4 smaller pixels into one big pixel, okay? And so what this does is it effectively makes the number of pixels that you have to read, divide that number by 4, okay? So if you have 1,000 by 1,000, but I'm binning those pixels, 1,000 by 1,000, that's 1,000,000 pixels divided by 4. Now it's only 250,000 pixels. And so now we can read them out even faster because we bundled those adjacent pixels and the charges that they captured. We bundled them together into one pile, one stack, okay? And so it takes a little bit, and the readout electronics have to be configured a little bit differently, and you have to have the right software code to execute the binning. But it actually streamlines the readout and makes it go even faster because, again, you're reading out less pixels. Now, what happens with this? Well, the pixel size is growing. Okay, so we're losing spatial resolution, but it's motion picture. And so this is 1 frame out of 30 that you're going to see in a second. Okay, and so it is going to look just a little bit fuzzier, but it's going to look like fluid motion because we can increase the frame rate with binning. Okay, and so there is some more fuzziness to the edge and a loss of spatial resolution, but the images are going by so fast that you don't really notice its impact. Okay, and so yeah, binning is special to digital technology. You can do it with a still image, but you're going to notice the loss in spatial resolution. It's really when we're in a motion picture loop and multiple frames per second, and the pictures are flying by your eyeballs so fast, and we're refreshing that screen with a new image very rapidly, that you're not gonna notice the loss of spatial resolution. Okay, and it's a way to make the software process images faster. Okay. All right, subtraction. Now the first time I gave this lecture, I thought I did pretty good with this. So temporal subtraction, that's time-based subtraction. What we do is and this is the first way we figured out how to do temporal subtraction. This is the original version of subtraction, okay? What we do in temporal subtraction is we take an initial X-ray, just a plain X-ray, okay? But it's digital. And so the colors that you see, the blacks and the whites and the grays, those are all really intensity values stored in computer memory, okay? And so what we can do is we can basically take the grayscale and swap it with the intensity scale. And so basically resave the thing as a negative polarity image, where everything that was colored black is now colored white, everything that was colored white is now colored black. You see this a lot when radiologists run fluoroscopes. You might notice, hey, that barium looks black. That's weird. Well, no, they've reversed the polarity. They've done the software swap and reversed the polarity of the image, okay? Like they're taking a mask, okay? And so the mask, we take the first image, the software does, and it swaps all the black colored pixels for white colored pixels. It completely reverses the grayscale in that image, okay? And then it takes a second image and a third image and a fourth. It takes as many other images as you want, but before it broadcasts an additional image, it subtracts away the negative polarity image. And so what you get is if the pixel is subtracted from its opposite color, it moves it to the middle of the grayscale. It effectively neutralizes the color changes from medium gray, and you just get this slate gray with X-ray with no contrast. Every pixel is colored the same color, the very middle gray shade in the grayscale. Okay? But now the magic happens, okay? If we make a change to those subsequent images, like introducing contrast in front, that changes the attenuation of the attenuation and the intensities of some of those pixels. And so now, instead of, so let's say medium gray is 0, and black is -10 and white is 10. So when I subtract a white pixel and I subtract away a black pixel, that's 10 minus 10, that's 0, okay? But now I have subtracted to 0, but now I inject in barium, or I have the patient drink barium, or I inject in iodine. Now the pixel's not at 10, now the pixel's at 15. So when I subtract away 10, now it's not broadcasting 0, middle gray, it's broadcasting something darker, okay? Because you're not broadcasting, because you've changed the subtraction formula by adding in an X-ray absorber. And so the X-ray absorber gets in front of some of those pixels and changes the intensity that you're measuring. So you're not subtracting away enough anymore to cancel out the pixel. And so the only pixels that show up are the ones that are enhanced by contrast. Okay? Yeah. The more modern software version of energy subtraction, and this is really neat, it borrows from bone densitometry. So in bone densitometry, to isolate bone tissue attenuates pretty well regardless of whether it's high or low X-ray, high or low energy, high or low kVp. It attenuates pretty well, okay? But soft tissue does not. contrast agents also attenuate pretty well regardless of its high or low energy X-ray. And so you can do a pulse of low kV beam, capture that image matrix, and then follow it with a pulse of high kV beam, and then subtract those two away, and what you're subtracting away is basically the soft tissue. And so the only thing that's left is good attenuating tissue, like contrast enhanced tissue. Okay? And so energy subtraction, right, while temporal subtraction is counting on the difference in attenuation of the tissue over time because you introduce contrast, energy subtraction is counting on the fact that there's a difference between how low kV goes through contrast enhanced tissue and high kV goes through contrast enhanced tissue. Okay, and so what you end up subtracting away a tissue type in energy subtraction, whereas you end up subtracting away all tissue except for contrast enhanced tissue in temporal subtraction. Okay, and so there's benefits of both. So one of the downfalls of temporal subtraction is motion artifacts. Remember, the way we do temporal or time-based subtraction is we take a picture at the beginning of the run, negate its polarity, and subtract it away from each subsequent image. Well, if the patient moves, well, then the pixels are misaligned and we're applying the subtraction wrong. And so you get these motion artifacts. It's called a mask shift artifact or motion artifact during a subtraction run. Okay, and that's why you can see the white edges of the shoulder and the white lung markings and even white edges to the ribs there. That's where the patient took a breath during the subtraction run. We're not supposed to see how everything kind of looks slate gray, but it's got these white streaks through it. The white streaks are not supposed to be there. The white streaks is because the images in the run moved a little bit relative to the first image. And so you're not subtracting away the same pixels from the same pixels. Okay? And that's why you get that variance. Okay? Now, they figured out that this was a problem for temporal software subtraction, and so they made... Alright, so the software correction that they figured out later, because motion artifacts were so troublesome with temporal subtraction runs, is that they allow you to basically mouse click with the arrow buttons and migrate the mask over to the new position where the patient moved to. And what that does is it basically eliminates those white line artifacts. Okay, and so that's a mask shift, mask adjustment. It's not perfect, but it's definitely better than having to do the run over again because the patient moved during the run. So it's a imperfect correction. It doesn't work like perfectly. It doesn't work exactly. It minimizes these white streaks that you see, but it doesn't completely eliminate them. Okay, and largely because motion is not true horizontal and true vertical. Motion is kind of in random oblique planes, or it could be a complex motion like an ellipsoidal motion, like you see in breathing. Okay, and so if the motion is just straight horizontal, straight vertical, yeah, you're going to clean it up real good with the mask shift software. But if it's not, and usually human body motions are not like pure linear motions in one direction or in two 90-degree vectors. It's a little bit more complex than that. It moves in random directions. That's the breakdown of the mask shift, okay? In energy subtraction, it's like you're taking a new mask every 2 frames. And so if the patient moves during the run, the mask moves with them because you're updating the mask every time, so to speak. So energy subtraction, you don't see these motion artifacts in the run. Okay. All right, our image display. For a conventional fluoro system, it was interlaced mode, which is, that's like for the display, for the actual TV screen. In the day, cathode ray tube is what I'm talking about. It would populate the image every other row at a time, okay? And then the signal to noise ratio was about 200 to 1. So it's decent, but it's not great, okay? In our digital fluoro system, it's a progressive display, which means it populates the rows sequentially on the monitor. So it changes the colors of the pixels in the top row of the monitor, and then it shifts to the next row down, and then the next row down. And it also does it faster than the CRT, the cathode ray tube. Okay. And then our signal to noise ratio on the digital fluoro systems are usually 1,000 to 1. So 5-time improvement in the signal to noise ratio with our flat panel detector system. Okay. And that's all we have for digital fluoro. Again, I did my utmost best to make this a remedial lesson. Okay. I am strongly thinking about giving you guys a replacement quiz for digital fluoroscopy. I don't know when that's coming, but it won't be a pop quiz. It'll be like fair warning. I've recorded this lecture. I've done my side, my heavy lifting to try to repair this because we didn't roll out this material the right way the first time. And so what really counts and what really matters is you got to have a fair assessment on it too. So sometime after the midterm, I'll announce that we're repeating the digital fluoro quiz, and I'm going to give you time to listen to this recorded lecture. So I'm uploading this Friday afternoon, the week before your midterm, in hopes that it can also help you study to the midterm. The other things I'm doing is I'm having the adjunct Ms. Smith, she's building you guys a Kahoot to help you study for the midterm exam. And so hopefully these two things and the ability to take the digital fluoro quiz again as not a pop quiz but a planned event with notice, and it completely is going to replace your earlier digital fluoro quiz. Hopefully that has repaired this course and taken up for the sloppy rollout of this course. Anyway, I do apologize again, and hopefully the remainder of teaching this course will be a little bit smoother than the launch of this course has been. So thanks guys, thanks for taking the time to review this course. I know you guys are busy too, and I really appreciate learning. You guys making the effort to learn the material really means a lot to me. So thanks again.